3:05, so let's get started. So just a few announcements. Quiz 2 is out. It was posted yesterday and will be open until Saturday night at 6, just like the first quiz was. Homework 1 is obviously out, so I would highly recommend you at least do at least a few of the problems so that you can get some extra practice. Quiz 1 solutions are posted, as well as solutions to the problems that we did last week in recitation, just in case you missed one. So, are there any questions before we get started? So if you have any questions at all, do you have anything related to material? Anything? Yeah.
Is the homework, if we don't do it this week for getting feedback, are we allowed to go to someone's office hours to get feedback on it if we do it at a later date?
Get feedback on it in terms of just a general strategy, I think would be the best. There's not a strict policy on that, but preferably we don't want to read through an entire solution. Just like, is this idea okay, would probably be the best way to go about it. Certainly if you submit before the deadline, then you'll definitely get full feedback on the whole thing. Any other questions before we start? One person says no, so therefore a majority say no, so. Yeah. All right, so last week, what was the major thing we were talking about?
DFAs.
DFAs in general, but in terms of, okay, we can make DFAs for some languages, but what things do we want to do to make new languages with DFAs? So how did we go about doing that?
These set operations.
These set operations, right? And what are the set operations on the language of the DFA? So what were the operations that we actually talked about? Union was one of them, yeah. What was another one? Intersection, yep. Concatenation, we started talking about, but we didn't get quite the closure under yet. What was the other one?
Star.
Star was another one, but we haven't gotten quite there yet until we got to NFAs. What was another one we talked about with DFAs? Starts with a C. Complement, good. Yeah. So that was the third one we talked about. And what do I mean by closed under these operations?
So when you do the operation, you're still in the linkage, it's still regular?
Yeah, very close. So if I have, say, a regular language and I find its complement, that is also regular. That's what close under complement means. For union and intersection, if I have two regular languages, whatever they may be, I form the union of them or the intersection of them, that's also regular. That's what it means to be closed under those operations. So let's figure out, why is that true? Why are these operations closed under, regular languages closed under these operations? So why is it true for complement? Why are the regular languages closed under complement?
Because we know that all you need to do to a DFA, which recognizes a particular language, is just make its accept states non-accept and its non-accept accept.
Exactly. So what I do is I flip the role of the non-accept and the accept states. Because we know that for a DFA, there's only one and exactly one computation. So it could only land in one place once we read it all. Therefore, if it was not accept before, just make it accept now. If it was accept before, make it not accept now. So we know how to do this one pretty easily. So how do we do union and intersection then? You might be in the way of the camera, just over.
Intersection is the union and the complement.
Yeah, so these operations are related via complement, but how would I even do, say, union? I need to have one first.
Union is just including but like if you have two sets, and union is making a new set that has all of them together.
Right. So I know what the operation is, but how would I do that with DFAs? Because if I want to show it's regular, I better produce a DFA for it. So let's say that I have two DFAs, and one which has some definition with ones in the subscript, and then two, which is twos in the subscript. Okay? These are just two arbitrary DFAs. And so now I want to make a DFA, let's just do union first, that recognizes the union of these two languages. Okay? So how would I define the pieces of this?
Make it ordered pair.
Oh, so something about ordered pairs. Why are we going to the trouble of going through something like ordered pairs? Why can't I just say, whatever input I have, feed it to the first machine, then feed it to the second machine. If at least one of them accepts, then I accept. Why can't I do that?
Because you can't get the input which you've read back.
Exactly. Once I read the input, it is gone forever, right? So I can't back up on the input. So I only have one chance to feed the input to both machines at the same time. So the idea was, let's just run them in parallel. But I don't really have a notion of running in parallel other than just running one DFA. So I got to make a DFA that simulates both of these, quote unquote, at the same time. So the idea was, let's just look at all ordered pairs of states in both machines. So how do I write down the set of all ordered pairs of states?
The set containing Q1, Q2.
Well, isn't that just the union of it?
It's ordered pairs though.
So
One Q cross the other Q.
Exactly. It's Q1 cross Q2. Right? This is just a set which has ordered pairs where the first guy comes from Q1 and the second guy comes from Q2. Right? Because I don't want to exclude the possibility, maybe some ordered pair I don't need. I want to include all the possibilities at the same time. All right? I think the alphabet's going to be the same, so that's no problem. I'm going to have some new transition function, which it seems kind of complicated, so I'm going to leave it out for now. I'm going to write it down here later. But now I got to figure out what the final states are and what the start state is. So I'm going to ask this question several times as we're doing this. What are the states of this machine? Corresponding to.
Ordered pairs.
Exactly, there are ordered pairs, right? Because it's just a set of ordered pairs. So I think for the start state, I better write down an ordered pair, right? Because it's the state of the machine. So I got to figure out what's going to go in each of those places. Well, how do I find that out?
You're looking at both of the transition functions.
Oh, well, not quite yet. Or not quite
Oh,
looking at the
looking for the
transition
initial
function.
states?
Oh, it's the start states of the original thing. I gotta figure out where am I in the first machine when I first start up this machine. Well, I'm in Q01 for the first machine and Q02 for the second. So I better write Q01, Q02 as the start state of this new machine because these are the start states of the original machines. And the final states seem complicated and I don't think I can fit in this small amount of room, so I'm going to write it down there. Any questions on that so far? Okay. So now I got to figure out what the transition function is. For an arbitrary DFA, what does the transition function take as input?
That's state and character. Well, that's
Yes.
this character.
It takes a state and a character in general. What are the states of this machine? Ordered pairs. So the thing that corresponds to the state when I feed it to the transition function better be an ordered pair, right? So I'm going to write that ordered pair as Q1, Q2. And let's say that the character I'm going to read is A. So what is the output of the transition function? A state. What are the states of this machine? Ordered pair. I think you get it by now, right? So I better write down an ordered pair as the output of this machine. Well, let's see. What is the first coordinate of the pair keeping track of?
Track of the ordered pair state, the ordered pair state that we're in.
Oh, well, that's the whole ordered pair, but what's the first coordinate of the ordered pair? Tell me.
It's the result from the first transition function.
Ah, it tells me what would have happened if I just looked at the original DFA, the first DFA, and just ran an input on that completely independently? What state would I be in there? And the second one tells me, if I ran just the second one, what would it have done? So how do I find out what happens right here? Well, what state was I in the first DFA? What state was I in? Well, I have an ordered pair here, Q1, right? How do I find out what the first DFA would have done?
Run that through delta 1.
Delta 1, the first transition function, right? So this first coordinate is going to be delta 1 of Q1 with A. What do you think the second coordinate is going to be?
Q2.
Yes, good. It's the second transition function with the second state. Good. Pretty straightforward. So now I got to figure out what the final states are. For any DFA, what are the final states? What is the structure of the final states?
It's just a subset of Q.
It's just a subset of Q, or in general, a set, right? So I better write down a set. What are the states of this machine? Ordered pairs. So F better be a set of ordered pairs, right? So I'm going to write down an ordered pair, Q1, Q2. So I got to figure out what has to be true of Q1 or Q2 in order to make this ordered pair a final state now, right? I better figure that out. But first off, for these first four parts of the definition, did that have anything to do with union or intersection? Did that have anything to do with it? No, I didn't say the word union or intersection at all. So the only change between union and intersection is the set of final states. So let's assume we're doing union, for instance. Well, what has to be true of Q1? If Q1 is a final state, are we in the union? Yeah, because that means that if we landed in Q1, Q2, and Q1 is final, that means the first machine accepted. But that means we're in the union. So that must mean clearly Q better be in F1 is a possibility. What if Q2 was a final state by itself? Do I care what Q1 was? No. It's the same thing with the original one. Oh, that should be Q1. If Q1 was final, I don't care what Q2 was. So I better have Q1 is a final state or Q2 is a final state for in their own DFA. Okay? So I better have at least one of the two parts of the ordered pair be a final state. And that's how I determine that this ordered pair is a final state. Any questions on that? Oh shoot, I forgot to tell you. I meant to do intersection instead of union. I just forget sometimes. Do I need to do this whole thing again?
Just the final state.
Oh yeah, the final states need to be changed. Oh, what do I change about the final states? In order to make it intersection.
So, the or.
Oh, I only need to change one word. I changed the or to an and. Well, there's obviously more complication than that, but it's very simple to change from union to intersection. Okay? Are there any questions about this? Okay, so let's actually do some of the exercises on the handout. On the back, there are 3 additional exercises. We're definitely not going to be able to do those, but those are just for your extra practice. And feel free to ask me about them if you have any questions. So we're definitely going to do the first 3 on the front, but we may do the 4th one if we have time. So the first one is, I want all the strings in 0, 1 star such that the number of occurrences of 0 is not 2. Okay? So any string that has 0 zeros, 1 0, or 3 or more zeros. I don't want any that have exactly 2. For some reason I hate 2. Okay, so how would I design a DFA for this? And the whole point of this recitation is to figure out how am I going to use these three operations to make my life as easy as possible. So do you think I could apply any of these operations to make this easier for me? Well, here's something that a first observer might see. This turns out to not be true, but if I have not equals there, that corresponds to checking whether the number of zeros is exactly 0, or 1, or 3, or 4, or 5. It seems like an infinite number of things I need to check. Not really, but it just seems like that, right?
So are you suggesting that we make a DFA that checks if you have exactly 2 and then complements it back?
Exactly, that's the idea. Let's make this as simple as possible for me. Let's change the condition to be exactly equal to, but then we have closure under complement, so if I make a DFA for the equals one, I can make one for the not equals one. Okay, so let's do that. Let's say L is the original one. So I want L bar, which is the exact same thing, but the number of zeros is exactly 2. Okay? Let's see. So how would I make a DFA for this? Well, I can check if it's exactly 0 zeros, 1 0, 2 zeros, but when I get to 3 zeros, should I ever accept? If I've seen 3 zeros, should I ever accept at that point?
No.
No, because, for the complement one. Because there's no way once I've read 3 to get back down to 2. So I should make states that correspond to 0 zeros, 1 0, 2 zeros, or 3 or more zeros. Okay? So I'm going to make 4 states then. So Q0, Q1, Q2, Q3. And the subscripts tell me how many zeros that I've seen. So what should the start state be? It should be Q0, right? Because if I've seen 0 zeros, then I should be in that state anyway. So I should be there. I'll do final states again, obviously. So now we got to figure out what the zeros and the ones are going to do. So where do you think Q0 is going to go on a 1?
Q itself.
It's going to read a 1. Where's it going to go?
Loop on itself.
Loop back to itself. And why is that true? Because if I see a 1, does that change the number of zeros that I've seen? No, that doesn't change the number of zeros. Oh, what does that tell me about the other 3 states on input 1? They're also going to self-loop. Good. 1, 1. So now I'm clearly not done. I have the 0 transitions left. So the transitions labeled 0. So where do you think Q0 is going to go on input 0? It's going to go to Q1, I hope, because now I've seen exactly 1 0. Where's Q1 going to go on 0? I think Q2 for that reason. Where's Q2 going to go on input 0? Q3, good. And where's Q3 going to go on input 0? Oh, wait, shouldn't there be a Q4? Oh, it just loops on itself because I don't care what happens after here. Good, so that should be a self loop. Okay? So, when we do closure under complement, do I change anything about the DFA other than the final states? No. So once I've built the states without the final states, I think I'm already set to do the original one, right? So let's just ignore the L bar for now and do the original one. So what should be the set of final states? Q0, Q1, Q3. Good. Those are my final states. And because, and we can check to make sure we're right, because if we invert the final and non-final states here, the only final state will be Q2, which is the exact condition that I wanted before anyway. So we really do have the right DFA here. Any questions about this? Again, two people say no. Oh, everyone says no there. All right, so let's move on to the second problem, which says I want all the strings in 0, 1 star with an even number of zeros, and the number of ones is exactly 1 or exactly 2. Okay? Does there seem to be any word that's very important in this definition? Oh, the and sounds pretty important. What do you think that corresponds to?
Intersection.
Oh, that sounds like intersection to me. So, what does that mean? If I can make a DFA for this part, and then a DFA for this part, can I make a DFA for the whole thing? I think so, because that's what closure under intersection means. If I have two DFAs, their languages are regular, therefore their intersection is also regular. Okay, so let's make a DFA for both. So let's consider L1, which I'm going to call the first part. So the number of zeros is even. How would I make a DFA for this?
We would have a DFA with the 2 states.
Oh, okay. Yeah, we actually saw that in class. Having a 2-state DFA, one corresponds to having seeing an even number of zeros, and the other one is an odd number of zeros. So I'm going to have a 2-state machine. I'm going to call Q even and Q odd. Okay. What should the start state be? Q even. Good, because if I've seen nothing, then I've seen 0 zeros, which is even, obviously. What should Q even do on input 0? It should go to Q odd, right? Because if I've seen an even number of zeros and I see one more, now it's in an odd number. What should Q even do on input 1? It should self-loop, good, because again, if I've seen 1 here, it doesn't change the number of zeros I've seen. Good. What is Q odd going to do on input 0? Q even, for the same reason. Q1 on 1? Again, it's self-loop. So this is a very simple DFA. Am I done here? Oh, what have I forgotten? Oh, final states. Okay. So what is the set of final states going to be here? Q even. Good. Oh, I should ask. If I just left it like this, what would the language of this DFA be? Non-regular? It's a DFA.
The null set.
The empty set. Yeah. So let me ask you an important question. Is this equal to this?
No.
A set containing one thing, a set containing nothing. Can they be the same?
Well, I mean, they don't have the same terminology.
They don't even have the same number of elements, so they can't be the same. So this is not the same thing as this. This has 0 elements, this has 1 element. But the element in here happens to have a string which has no characters in it, but it is something, right? Is this equal to this? No, for the same reason. This set has 1 element, which happens to be empty, but this one doesn't even have anything in it.
Well, the thing on the right is a set containing a set.
Yeah, well, this is a set too, but this just has 0 elements, this has 1 element. The element in here happens to be a set which has nothing, but it is something. Okay? So it's just important to know the difference between empty set and empty string, but just a minor point.
So then is the language empty string or empty set?
Empty set. Because I feed an empty string to this and see what happens, but the language, the set itself is empty. Because language is just a set of strings, right? Because language is defined to be a set of strings. It's not a string itself. And so they're not even comparable. But we already agreed that this should be the final state, Q even. Okay? Cool. So now let's make a DFA for the second guy. So I'm going to call L, spell L right, L2, which is the same thing, but the number of ones is exactly 1 or 2. So how would I make a DFA for this one?
Your states 1 with 0, 1 with 1, 1 with 2.
Well, I gotta make a single machine. And once I get to 2, well, I want exactly 2. I don't want at least 2 here. So what can I do? Does this sound a little familiar? Yeah, this, if you ignore the 1, have we made this DFA before? Or a related one? Yeah, we made it right here. The complement of it, but we made this DFA pretty much right here. Okay, well, what was the complement of this DFA? It's the exact same thing, but this state is the only final state. If I change this, the complement one, to say 1 or 2, what would the final states be? If it was just, instead of just Q2, what would the final states be? Q1 and Q2. Okay, so maybe I can use that DFA related down here. Oh, wait, this says number of zeros is equal to 2, but this one says number of ones. It seems hopeless, right? What can I do? Oh, I can switch the role of 0 and 1. Okay, so that sounds fun. For some definition of fun. All right. Q3. Q0 is going to again be the start state. So where are the 1 transitions going to go? Are they going to go across the states, or are they going to be the self-loop states? The self-loop transitions. Then move to the next state because they're taking on the role of the zeros from before. Good. And Q3 again is going to loop on 1. What are the yeah?
Do we need Q3 here? Why are we using it here? I mean, what if we just finish on Q2?
The Q2 because I want exactly 2. What if I read a 1 in state Q2? Like. Then at that point, I've seen 2 1s, but then if I read another one, now I've seen 3 1s. Where am I going to go? Yeah, so you need an extra state there.
Okay.
Yeah. But where are the 0 transitions going to go?
Loop on themselves.
They're going to loop on themselves because they take on the role of the 1s up here. Good. So 0, 0, and 0. Oh, and Q3 is 1. Okay. Am I done with this DFA? Oh, what have I forgotten?
Final state?
Oh, those pesky final states, right? So what are the final states going to be here?
Q1 and Q2.
Q1 and Q2, because those are the conditions I want to accept for. All right. Now, which is good. Am I done with the whole problem, though? Oh, wait, what have I forgotten?
Intersection.
Oh, I need to do intersection. Okay, so now I gotta do something related to this process. I want to make a DFA for the intersection of these 2 languages. Well, the languages of these 2 DFAs. Well, how many states am I gonna have? I gotta make these ordered pairs. How many states am I gonna have? 8. And how do we know? I gotta make an ordered pair with even as the first coordinate, 0, 1, 2, 3 as the second coordinate, odd as first, 0, 1, 2, 3 as the second coordinate. So I'm gonna have 8 states. So I'm gonna have Q even. Oh yeah, so this is the notation that I use to make it easy for myself. I have 2 subscripts. The first one comes from the first DFA, second from the second DFA. So I'm going to have a Q even 1, Q even 2, Q Q even 3. Then I'm going to have a Q odd 0, Q odd 1, Q odd 2, Q odd 3. Okay? It's just enumerating all possible order pairs between those two sets. Okay, so I know the set of states now. I know the input alphabet. So now I just got to find out what those other three are. I'll do final states last. What is the start state going to be? Well, let's look at how we did it over here. It's the start state of the first machine with the second state of the second machine. Oh, what's the start state of the first machine? Even. Start state of the second machine is 0. Okay, so I think the start state of this new machine better be even 0. So that's my start state. Okay. So let's figure out what the transitions are going to do then. So let's figure out in Q even 0, where am I going to go on input 0, for instance? So in my mind, I'm going to keep track of where I was in both machines and where I'm going to go to on the same input. So I'm in even before and 0 before. Where is even going to go on input 0? Odd, right? So in my brain, I'm going to write down odd, the word odd. 0, Q0 on 0, where does that go? Goes back to Q0. So I write down 0 in my head. So I've now written down odd 0. Do I have a state for odd 0? Yeah, I have one right there. So even 0 is going to come to odd 0 on input 0. All right, let's do even 0 on input 1. Even 0 on input 1. Where is even going to go on input 1? It is going to stay even, so I'm going to write down even. Q0 on 1, where does that go? It goes right to Q1. So even Q1. Oh, and I have that state right here. Good so far? Let's do odd 0. Odd 0. Where is odd 0 going to go on input 0? It's going to go back to even, so I write down even. And then what else do I write? 0. So even 0. It's going to come back here. Where's odd 0 going to go on input 1? Well, if I'm here and here, where's odd going to go on input 1?
Loop on itself.
It's going to loop on itself, so I write down odd. Where's 0 going to go on 1? It's going to go to Q1. So I better go to Q1. And at this point, they're like, oh, we have 12 more transitions to do. Is there any kind of pattern that we can deduce so that we can make this easier for ourselves? Is there any pattern that you can see?
I mean, if there's in each of the even or odd rows, if we increment the 1, it'll change the parity of the zeros.
Oh, okay. So let's think about that. Let's think of the 0 transitions. If I'm in this machine, no matter what state I'm in, I'm going to switch to the other state, right? So no matter what row I'm in of this DFA, which corresponds to this first DFA, I'm going to switch the row, right? So if I'm up here in some state up here, I'm going to end up with some state down here, and vice versa. But do I stay in the same column? Well, here in this second DFA, I self-loop on every single state. But that means that since each state here corresponds to a column here, I'm going to stay in the same column. So I switch switch rows, but I stay in the same column. So what do you think Q even 1's going to do on input 0? It's going to go to the odd row, obviously, but it has to be in the 1 column. Odd 1, where's it going to go on 0? 1, good. What about the 2's column? Where's that going to go on? Where are those two going to go on 0?
We're gonna reflect on each other.
They're going to go between each other on 0, good. And what about the 3's column? Same thing. And now I'm just going to note, not all DFAs, pairs of DFAs are going to have a nice pattern like this, but it's nice to see that we were able to deduce that pattern. Okay? Oh, maybe let's try something with the 1's. Maybe there's some pattern with the 1's. Do you see a pattern with the 1's? Well, let's think. Let's think about both DFAs. What am I going to do in the first DFA on input 1? I'm going to always self-loop on whatever state I'm in the first DFA. So what does that mean? I'm going to always stay in the same row when I'm reading a 1. Always. What about the second on 1? Well, no matter what state I'm in, I'm heading toward Q3. Right? So if I'm in Q0, go to Q1, Q1 to Q2, 2 to 3, 3 to itself. So what do you think even 1 is going to do on input 1? Even 2, because it has to be the same row, and it adds 1 to the number. Odd 1? Odd 1? 2. Odd 2. The 2's column, where do they go?
3's column.
The 3's column, same row, good. Oh, wait, shouldn't there be some 4 column?
No.
No, why?
Because you just loop back to the 3 column.
Why do we loop back on ourselves? Because in this DFA, the first one, we always are self-looping on input 1. But in Q3 over here, I also am self-looping. So in those 2 states, I'm going to also self-loop on 1. Okay? Am I done? Oh, I keep forgetting the dang final states. All right, so let's figure out what the final states will be here. How do I find that out?
The first one and the second one?
Yes. Because we're doing intersection, both parts of the pair must be final states. So it must, well, the only final state in the first guy is even. So the first coordinate better be even, and the second one better be a final state. Well, the only final states are 1 and 2. So the only final states are?
Even 1,
Even 1.
Good. Even 1 and even 2. Perfect. Okay. Any questions about that? Pretty simple. It's just seeing what you would have done in both DFAs. All right, let's do number 3. So it says, I want all strings in 0, 1 star such that the number of zeros is even, or the number of ones is not a multiple of 3. So a lot of people get confused by this. I'm not counting the binary representation of W. I'm only counting the number of ones here. So I don't care about the zeros in that case. But what is the most important word in that definition? Or, yeah. So what does that correspond to? It sounds like union to me. So let's make a DFA for the first part and then a DFA for the second part. So can I make a DFA for the first one? Oh, yeah. So we've already made a DFA. Let's just copy it over. So I'm going to call L1 to be the number of zeros is even case, and that's just the DFA we had. All right. So that's just copying the DFA over. So the whole point of this is to see where you can see making things a lot easier for yourself, whether it be patterns or using DFAs you already made, or actually using smaller DFAs to make larger ones. Okay? Does anyone need the 8-state DFA that I just drew? Okay. Because because I need extra room for this one. So now we want to make a DFA for not a multiple of 3. So when you see multiple of 3, what do you immediately think for DFAs? Oh yeah, this 3-state thing, what does that correspond to?
Remainders.
The remainders, right? Because with 3, there are only 3 possible remainders, 0, 1, and 2. So let's make a 3-state DFA. So I'm going to draw this vertically for a reason you'll see in a second. So the 3 states are going to be Q0, Q1, Q2. What's the start state? Q0. Yeah, because if I've seen 0, 0, well, I hope 0 is a multiple of 3. All right, what does Q0 do on input 0? It loops on itself. Good. And why is that? Because it doesn't change the number of ones we've seen. What about, oh, wait, then what can we say about Q1 and Q2 on input 0? They're going to loop on themselves also. Good. Now I just got to figure out what the 1 transitions do. So what do you think Q0 is going to do on input 1? It's going to go to Q1 because if I have a multiple of 3 and I add 1, now the remainder is 1. What about Q1 on input 1? Q1 on input 1. Go to Q2. Exactly. Oh, wait, shouldn't there be some Q3 for Q2 to go to? No, why is that? Yeah, we're only doing a remainder. So if I have a multiple of 3, then I add 3, now I still have a multiple of 3. So Q2 better come back to Q0 on input 1. Okay? Cool. So, am I done with the whole problem then? Oh yeah, again, final states. So now I got to figure out how do I find the final states of this 3-state DFA?
The ones that are not.
The ones that are not Q0 because that's the multiple of 3 condition. So I'm going to make this one final and this one final. I could have done the complement of that and then flip the states back and forth, but this was a lot easier. Okay, so now I actually do have to do the product construction here because it's union. So how many states am I going to have? 6, because 2 times 3.
Oh, I see what you do.
Yeah.
And then like make an array.
Yeah, so the way the reason why I did this horizontally, this one vertically, means that this row corresponds to Q0, Q1, Q2. This column is even, this column is odd. So it makes seeing what happens with the transitions a lot easier. So let's make the states then. Q even, 0, Q odd, 0, Q even, 1, Q odd, 1, Q even, 2, unless I made a mistake, odd, 2. Okay? So what's the start state going to be?
Q0 even.
Q0 even, good. I'm going to leave final states to the end. What does Q even 0 do on input 0? Well, it's a lot easier with this diagram, the way I set it up, because I just look at what happens in terms of columns and rows. Here I'm in the evens column, and I read a 0, I must go to the odds column. And here I'm in the 0 row, and I read a 0, I stay in the 0 row. So even 0 goes to odd 0 on input 0. Okay? Where does even 0 go on input 1?
Even.
Well, must stay even and go down 1 row. Because Q0 comes down to Q1 on input 1. So it comes down. Odd 0, where does that go on input 0? let's think. Where does odd go on input 0? Goes back to even, so it's going to come over here somewhere. 0 goes where?
0.
Goes back to 0, so I come back over here. Odd 0 on 1, where's that going to go? Well, odd loops itself on 1, so I'm definitely going to be in the odd column. But where am I going to go on input 1? On 1. Odd 1, because that DFA comes down to 1. So I come down. Again, DCA is happening. Is there a pattern here?
Yeah.
Yeah. So let's think. This one's going to, again, switch between the odd and even column. And for that DFA, it's just going to stay in the same row here. So I think the 1s are going to go across here on input 0, and the 2s are going to go across on input 0. Just like before. Almost no change. Okay? What about the 1 transitions? Where are they going to go? Well, let's think. In this DFA, it's going to stay in the same column. So no matter where even 1's going to go, it's going to be in the evens. Where does 1 go on input 1?
2.
It's going to go down to 2. So it must stay in the same column and go down to 2. So I better come down here. Am I done? Oh, I forgot final state, but have I forgotten anything else?
Q2.
Oh, the 2 transitions on 1. Where do they go?
Back around Q1.
Oh, they stay in the same column, but they come back to the 0 row. Good. Okay? And then now we got to find final states. So what operation are we doing again?
Union.
Union. So how do I find what the final states are going to be?
The state that is accepting in either L1 or L2.
Oh, okay, so either L1 or L2. Well, that means that any state with even, should I make that a final state? Yeah, because if I was in even, no matter where I am over there, I'm still in the union, right? So all the even states are going to be final. Every one. Okay? Oh, am I done? No, because that means that every state that has Q1 in it must also be final. Oh, that must mean odd one's final. Even one I already marked. Q2, I better mark that as final also. And that one's already marked. And that's the effect. Okay? So I only have a tiny bit of time, so I'm not going to be able to do the fourth question, obviously. But I'm going to try to model it a little bit. So look at the fourth question. What do you think is the most important phrase of that question? But not both, right? That seems to be more important. We already know how to do or, but not both seems a little bit more strange. So let's modify this one and say, but not both. So do I need to do this whole thing again? I hope not. So what would I need to change?
Just take the intersection of final states instead.
Ah, yeah. I only need to take the ones where both conditions are true. Well, when both conditions are true is the intersection. So how do I find what the intersection of these, the states which are the intersection, the final states? Well, it must be even and be 1, or even and 2, right? Those are the only states in the intersection that are final. So what do I do here? I take them out when I have but not both. So this one is not final anymore. And this one's not final either.
So doing the but not both just subtracts the intersection.
Yeah, so whenever you have or but not both, just means whatever the final sticks are for the union, take out the ones that are intersection. And then now you got the final sticks for this one.
So that's like an exclusive order, I guess?
It is exclusive form. Yep. That's what's called symmetric. I think that's what's called symmetric difference. Yes, that's what's called symmetric difference. Any other questions? I'll see you next week.